Thank you so much. Thank you, David. Can you hear me okay? Is this good? All right, excellent. All right, the slides, there's a lot more material than I could really present here. So the slides are all online, and if you use this QR code, this URL, you can get more background information, a lot more links. Everything is hyperlinked. And generally, I'll keep curating this, adding to it. This has kind of been a work in progress for the past couple of years. First off, though, let's see if this works. Something worked. Yeah, okay, great. I don't know, has anybody else seen this image going around the internet yet? Definitely some people are shaking their heads. So this comes from a system called DALL-E. And you'll probably see more of this, but it's a play on words from Salvador Dali. But it's a kind of neural network that associates different images that are found online with different texts that are surrounding them. So here, somebody made this. This was synthesized using DALL-E Mini, and all they had to do was just type the sentence at the top. Trail cam footage of Gollum eating watermelon. And the thing is that just by simply changing the words, you can get the system to, transfer, basically render a different scene. So, this is a good illustration of, say, transfer learning based on deep learning. Here I did Gollum eating watermelon, but inside of the movie Toy Story. And in celebration of coming here, I did, here is Gollum eating watermelon in Coruña. So you see there on Playa de Riador. Really interesting work, and I guarantee this actually does kind of fit in. So the talk is about graph data science, calling it graph thinking. And actually, these images down here were also generated by DALL-E Mini. It's a service that's provided by Hugging Face. You can download it, run it off GitHub as well. But this is, if you put in terms like graph data science or graph thinking or graph neural networks, DALL-E will just synthesize these images. So I kind of like that. There's a couple of networks there. Obviously, there's a woman who is definitely thinking about data science to some degree, and this just all was generated off of what were found on the internet. So as far as who I am, I've got some background there. I've been working in machine learning for about 40 years, and along the way, I got to do some fun things very early in the days of cloud computing and Hadoop and Spark and whatnot. These days, I'm at Derwen, and we work mostly in open source integration for engineering work on AI applications, mostly in European manufacturing companies, actually. And this talk here is about graph data science. This is an image from, I think, about 12 years ago. But back around 2008, 2009, DJ Patil, who is the cowboy over on the left, DJ Patil and Jeff Hammerbacher, who was at Facebook at the time, they started popularizing this term, data science, and there were some people who were identified as leading data science teams. And the talk today here is about graph data science and how this area is becoming distinguished, differentiated from, say, more of the mainstream work in data science. Being able to leverage graph technologies for industrial problems at large scale, it leads to very interesting kinds of applications that are needed today. It also leads to a lot of mathematical complexity, and it's really challenging for the current state of hardware. It's an area where quantum computing is expected or anticipated to probably be contributing a whole lot because of how much this area stresses things. First off, though, to introduce, I will present a little bit of a vignette here of a cognitive way to approach using graphs for data science. And so here, imagine that you're in a medieval village somewhere in the Black Forest in the middle of Germany. And there's a village, a very small village. There's someone named Pat who runs the pub. And Pat has two friends, Hannah and Thomas. And Hannah also, she works the fields, she raises grain. She has a friend named Aiden. Thomas raises poultry, to provide eggs. Thomas buys grain from Hannah. Thomas has a friend named Brenda. And then Aiden works the mill. He buys grain from his friend Hannah, and he produces flour. He has a friend named Chris. Brenda works the brewery. She buys grain from Hannah. She has a friend named Kim. Kim has a bakery. So he's buying eggs, he's buying flour, he's producing bread, which goes back to Pat at the pub. And Brenda's brewery, of course, also produces beer that goes back up to Pat. And then, the brewery and the bakery, they both produce some organic waste, which go to Kim. Kim runs the recycler. And so you can see this kind of circular economy developing just even in a real simple medieval village, just with 7 people and their businesses, the cottage industry. And one thing that I've seen a lot is that when I present this story, present this image, people who have business experience, one of the first things I hear back is, Hannah's going to make a lot of money. Because people who have that kind of business experience, they can see where the bottlenecks are in this diagram, and who is it that is most central, and who's going to be making the most deals. And so it's clear, Hannah is really poised to make a lot of money out of this village. Now, that has to do with patterns. And one of the problems that we see in computer science, of course, is for several decades now, actually, since the 1990s at least, we've been doing most of our data management based off of relational databases. And so if you were to take this graph and put it into normalized form for a relational database, you end up here with an entity relationship diagram showing 6 tables, the different primary keys and foreign keys and whatnot, the relationships between them. And when you look at the data put into those tables, it's not something that you can readily discern in terms of the patterns. If a business person looked at those tables in a spreadsheet, they would not necessarily tell you that Hannah's going to make a lot of money. And so one of the problems here is that if we use a relational database as our primary mode of interaction with the data, we lose the perception of patterns, and it moves it further away from the domain experts who can really solve the hard, complex problems. So instead, this area of graph data science is largely about taking these kind of network views and bringing the data in that form back closer to the people who really know how to make sense out of it. And there are 3 key points. One is acknowledge complexity, and also identify emergent pattern, and then make informed decisions based off of, again, this kind of network view of things. And of course, we talk about this day to day. We talk about supply networks, how complex it is these days with global supply networks, definitely. That's one good example. So I'll just run through a few notions here from graph data science. So Hannah is relatively new in the village, but she's doing well. She'd like to expand her business. She's noticed that her customer, Brenda, buys a lot of brain. So one question to pose is, how can Hannah identify other villagers who are similar to Brenda? How can she leverage the graph and find other opportunities to expand her business? It turns out that Chris, who runs a bakery, he also sells product to the pub, to Pat, and he sells organic waste to Kim. So Chris's activities in the graph look a lot like Brenda's. Maybe the bakery could buy raw, unmilled grain directly. Maybe they could sprout it, and make malt or something. And so that's one way that Brenda could expand. Hannah is also interested in doing a medieval co-marketing campaign to try to drive more demand. So, she can work with her direct customers, but can she identify who are the customers of her customers? And so if we take a look 1 hop away, basically 2 hops in the graph, then we can see that Chris, Pat, and Kim are also the customers of Hannah's customers. And so maybe, again, she should think about selling directly to Chris, doing some business development there. So these are ways that you can think about being able to leverage a graph in business. Now, kind of a fanciful notion, but okay, we have a tech billionaire. They use time travel to go back to medieval villages, and they want to figure out which businesses to acquire to leverage the situation. So what would be the best acquisition targets here? And if you run graph algorithms on this data, if you use, for instance, there's an algorithm called centrality, there's a variant of it called betweenness centrality. It's a lot like PageRank, actually. If you apply that to the graph, you find that Hannah and Chris are the top 2 nodes in this graph. They're the most central. And so they would be, obviously, pretty good targets for acquisition. And we can go on and on. If we want to add more nodes to the graph, we can sketch out like what would be some good ways to do some planning, contingency planning here. There's a lot more details. If you want to go in, Jürgen Müller, who leads knowledge architecture at BASF, Jürgen and I put together this example. We've been working on a lot of infrastructure together. Also, there's some discussions within Lorica and Gen Web. We have some podcast about this. And we try to dig into a lot more detail, a lot more use cases. Now, I want to change gears a bit and talk about something from 1999. David Snowden was at IBM's consulting business then, and he came up with a framework called Cynefin. It's a Welsh word. It describes a business context and then what types of decisions need to be made based on the complexity of the business context. And this is very salient for us in data science because we're supporting business decisions so much. So this was picked up and unfortunately popularized by Donald Rumsfeld a few years later after 2001. But it starts out in a simple business context. There's very clear deterministic cause and effect. And so really not a lot of expertise is required. You just identify what the facts are, you categorize what the needs are, and you respond based on rules. Best practices, basically, fit this. And that's known knowns. Spreadsheets are a good example of how to work with this kind of data. If you get into a more complicated context, then there will be variables, and you have to do analytic solutions to solve for variables within the context. And so this is where leaders turn to data analysts and the whole history of business intelligence. This is where you have to get in and assess the facts, try to understand them, not just use them directly, but really test them, and then go in and do some expert analysis, and from there come out with recommendations for the leaders to use, usually based on trade-offs. These are the known unknowns. And then the part that became infamous was where Rumsfeld used this, the unknown unknowns, where they aren't just simply analytic variables. When you get into a complex business scenario based on Cynefin, then determining cause and effect is very difficult. You can't do it reliably through reductionist means. But what you can do is understand emergent patterns, and then from the patterns be able to probe the situation, possibly doing some experiments, but really allow the experts, the leadership, to get a sense of what the situation is based on those patterns. There's another kind of scenario defined by Cynefin, and this is chaos, where there just really is no cause and effect. And the best you can do is try to find out where there might be some islands of stability, or run, depending on the situation. So I'll just leave a placeholder there. I think that Cynefin provides us with something very good in business when we're talking about complexity and decision making. Now, I want to compare and contrast with something that Susan Ambrose did about a decade ago. It's a book called How Learning Works. It's a really good introductory text on pedagogy if you haven't seen it. But in one part, she's describing some of the cognitive science to describe how it is that people progress from being a novice in a particular topic, going through different identifiable phases until they become expert in that topic. And so based off of that framework, and this is not AI, this is just simply cognitive science about how it is that people learn. So when someone is a novice in a field, they don't really have a mental model. At best, they're starting out learning some simple facts. And, there's not a lot of context here. There's really not a lot of ability to work with uncertainty in the data. It's just a matter of learning some of the facts. As people progress in a topic, they begin to see associations between the facts and start to build up chains of association and build mental models based off these chains of association. And this is where you can start to pose it some questions and do some queries essentially on the data. And now, as people progress into becoming more of a practitioner and becoming more competent in a topic, then they begin to have mental models that are very similar to, in computer science, what we call decision trees. And at this stage, someone can become much more advanced. They can work their way through a hierarchy of rules to be able to formulate a plan based off of data. They're able to work with more uncertainty. And this is, again, a practitioner's level. But when people get to an expert level, something interesting happens. They begin to learn ways of not following the rules. They have a mental model of the decision trees and the rules, but they also know where they break and why, and when to allow that kind of breakage of the rules. And so they end up with mental models that have links from some of the leaf nodes back up into other parts of the hierarchy. Essentially, you get a graph. And so the cognitive model for expertise is defined by a graph. And at this stage, experts do this kind of pattern-based sense-making. They leverage emergent patterns in the graphs. And so, these two come together then. If you think of like Cynefin and the business context of complexity in data and decision-making, and you compare it with what we know out of just cognitive psychology and how people learn, you can start to see how this applies then. If you have a really simple scenario and you're just applying best practices, you can probably just look up the data in a spreadsheet. And a lot of people do. When you get into something more complicated, you'll probably use a data warehouse. And you'll have some analytics on top of that. And that's been the history of business intelligence for a couple decades. But when you get into more complex kinds of patterns, or complex kinds of scenarios in business, you must rely on this kind of pattern-based sense-making. And this is where we are in 21st century with a lot of problems that we have these days in terms of global supply networks and pandemics and all the rest. It's really begs using something on the level of graph patterns. Now, there's sort of a contrapositive here. The opposite of this, though, is there's also, from cognitive psychology, this notion of ambiguity aversion. And we do see this a lot in industry, even at senior executive levels, where a lot of people have almost a visceral urge to avoid complexity, to avoid uncertainty. And even people who are top-level executives will make the wrong decisions just to avoid uncertainties. And this is a very dangerous kind of cognitive bias that we're seeing in today's world, again, with so many complexities. There are people who are lecturing and showing much better examples. As Cassie Kozakov out of Google is doing very good work here. So I've linked toward some of her material. And so that leads us then to how can data science really help and augment the decision-making that must be. And so this leads into how do we work with graphs, and if we're going to be providing AI applications in the context of graphs, then we're doing inference. So currently, there are a number of different ways to apply inference in graphs. Up in the top left corner, there are more axiomatic ways of, very explicit forms of inference. But there are other things that can be done. There are query languages for working with graphs. There are graph algorithms. We saw an example of that before. There are people doing a lot of visualization work. There's a lot of graph neural networks work, leveraging deep learning. We'll take a look at that more. The problem, though, is that these are different camps. And historically, they present at different conferences. So the work coming out of academia and research, these camps, they don't talk with each other. If you go and use their software off of GitHub, their open source projects don't have integration paths. And so it's very difficult to build an application that says that, for instance, makes it leverage of some sort of axiomatic approach, like closure for inference. But then it also provides capabilities for visualization and graph neural networks. You can't find that product off the shelf. And yet, this is a hurdle to overcome if we want to build out AI workflows, especially leveraging the current generation of hardware and looking toward newer forms of hardware. So historically, one of the problems has been there's this area of math, algebraic graph theory. It's very, very foundational for us. You can take a graph that's very rich and represents the real world and has a lot of interesting data. You can take it and simplify it into a vector form, vectorizing a graph. That's been done for a long time. A vector is a kind of algebraic object. You lose information when you do that, but you can manipulate things in a vector much more readily. Another kind of algebraic object is a matrix, and so you can also take a graph and project it into different forms of matrices, adjacency matrix or transition matrix. There's a lot of that kind of work that's been done. A better way, you still lose information though. A better way is to take a graph and put it into a tensor, which is a much more reliable kind of representation. You don't have the information loss. When I was doing lectures about data science and machine learning and doing training in industry, even as late as, say, 2014, when I got to the part about talking about graph algorithms and leveraging graphs, I would say, you know, there's something called a tensor. It's really useful. People would usually leave the room, right? They didn't want to hear about graphs. They didn't want to hear about tensors. That all changed about a year later because suddenly everybody was talking about TensorFlow. But it's interesting that you know, we've had this math for a long time. Really, though, we've been leveraging the matrix part of it. And so there are tricks for factorization. Non-negative matrix factorization is very popular. You can convert a graph into a matrix, and then you can do different types of transforms on the matrix. And there's some fantastic work in this area, but it doesn't really fit what we need to do going forward. And so here's a chart of some of the graph work over the past couple of years, just papers that are showing up on arXiv. And graph algorithms, graph neural networks, you can see there's quite an uptick. There's been a lot of healthy publication there. So graph neural networks are really interesting because, you know, when we talk about how do we make sense out of emergent patterns, this is exactly where deep learning comes in. And as I was trying to show earlier, you know, with Gollum eating watermelon on trail cam footage, or, you know, in the movie Toy Story, or here on the beach, Riazor, neural networks are really good for discerning patterns with high-dimensional data. It's a really excellent tool for that. And so graph neural networks, of course, have been on the rise. One of the foundational papers was Michael Brunstein out of London, 2016. One of the better papers I'd recommend them now, I don't know if the pointer works, but a friend of mine, Inez Chami, just got her PhD at Stanford. She has a survey paper about geometric deep learning and hyperbolic deep learning and just everything in the continuum there. I would definitely recommend her paper as a starting point if you want to look deeper into graph neural networks and where this is going. Another friend is Maciej Besta. He's at ETH Zurich, really doing fantastic work there, supercomputing facility, and a lot of work in terms of motifs, working with motifs, which is if I were to take the embeddings that are used in graph neural network, if I take the representation, and I apply supervised learning to find patterns and identify them, and maybe predict patterns or missing elements of patterns, that's typically referred to as motif prediction. So Maciej is definitely working in that area. And there's some great open source like DGL and GraphGem and others. Great. Okay, so there's a mini book. Dean Wampler and I wrote this for NVIDIA last year that really tries to explore some of these issues about where we are with data science and how hardware is becoming much, much more of a factor. And so the book is called Hardware is Greater Than Software is Greater Than Process. And it's talking about hardware being a driver for a lot of what we're doing these days with data, which is such a change in thinking from just 20 years ago. So it's sort of an antidote to some of the agile thinking in software, if you will. But it's very much, we tried to show examples based off of rapids and what's going on with the GPUs. A lot of what we're seeing there, of course, also applies to other types of hardware, different forms, definitely, but certainly with quantum computing coming up, I think a lot of this will apply. So the point there is that when we're working with graphs, we don't want to do just numeric. Numeric approaches like factorization have been very popular, but they also throw away information. We need to leverage graphs that have both numeric representation and symbolic. We need a kind of hybrid AI approaches. The numeric side is great if you're doing visualizations or doing graph neural networks, and you need that. But if you're working with natural language or regulatory compliance or human in the loop, anywhere that you're working with domain experts, you need to have the symbolic representation in there too. So it's very important to be able to switch back and forth between numeric and symbolic. And this is one area where graph data science is really differentiating, being able to incorporate both of these, because earlier approaches generally would just focus on the numeric side. And so that's where here, if we take these different camps in the graph technology space, we can map them out. There's definitely great open source work. Axiomatic side has W3C. There's so many different projects under the semantic web umbrella. Graph algorithms, of course, has NetworkX and iGraph, cuGraph out of Rapids. And then, there's a lot of different query languages. We'll talk about some of that. If you go into just, say, for instance, traversals, simple large-scale traversals of a graph, like with bulk synchronous processing, you can use Spark for that. Works quite well. Graph neural networks, there's a whole ecosystem emerging over there. Visualization, there's things like DataViz and Graphistry and PyViz. And then you've also got probabilistic graphs, a whole area of statistical relational learning that's been emerging. This is where you get into things like Bayesian networks and causality and a lot of super interesting work there. But the problem is, how do we find ways to integrate these together? And so that's one project that's been going on. I'll talk about that in a bit. The reason for doing graph data science is really the AI workloads require working with complex graphs and being able to blend between some of the more numeric methods and the kind of domain knowledge that you need. There's been a lot of difficulty with this, though, because the graph-based approaches, again, like I say, these areas are balkanized. They don't really talk with each other well yet. But there's a lot of opportunity to leverage what we know about the newer hardware and what we can do with distributed systems at scale, how we can apply advanced math to that. It's very well suited for parallelization with techniques like Ray and Dask and Rapids just off the shelf. Now, the difficulty, though, is that graph work is provably hard. In terms of NP completeness, you can show from the basic examples of proving that an algorithm is hard. Graphs are typically what you use. And so you can see where in typical graph use cases, if you're just doing some sort of path algorithm, that could be like order n log n, if you're doing something with Dijkstra or a variant of that. Now, if you're doing something with a large graph where you have to do a lot of pathing, like you have a graph query and it has unbounded paths, so that means I'm iterating through all the possible cases. Now you can get into n squared log n. If you've got a complex query that has multiple clauses that have unbounded paths, which people usually do, then you can get into areas of like order n cubed. And trying to run order n cubed algorithms on a graph that has trillions of nodes, that is more than our current computing can handle. There are ways of leveraging some of the math. Like, for instance, if you do have some graph theory background, you can take your regular data and do some data preparation. Although in this case, maybe you would do something like using a chordal graph and sort of reconfigure your representation, if you will, into something that's easier to solve. And this is where some of the graph neural networks really come in brilliantly, to be able to do link prediction and clean up the data, get it into a form that is more easily computable with. The problem is, though, currently we're still at a point where the graph database vendors aren't up to speed on the math, and we have some pretty good examples of that. IT industry really hasn't caught up yet. So, the thing is that there's a lot of areas where you can really leverage the math, certainly with graph theory and linear algebra, but also a lot of category theory comes in terms of being able to define what I don't have to compute. So that if I do have an order n cubed problem that's measured in billions or more, I can just avoid large areas of potential computation. And so that gets into the practice, what we see in industry. So our team has been working for the past couple of years. We've been working in manufacturing. And we've been working with teams at 3 different large manufacturers in Europe, mostly based in Germany, but some with very large operations here in Spain. So a knowledge graph is this term it's kind of abused. It's thrown around a lot, but the idea is you've got some kind of entities, some nodes, and you have relations between them, some sort of edges in the graph. You may also have attributes, either on the entities or on the relations. And all of the above may have probabilities assigned. It may be probabilistic. Typically, we use something called a controlled vocabulary to describe shared definitions of how to describe these different elements. And when you put a number of controlled vocabularies together, you end up with an ontology, or you end up with a way to thread different relations through an ontology that leads to taxonomies. And there's a lot of different vocabulary here, but the bottom line is if you've ever done any work in object-oriented programming, say in Java or C++ or even like TypeScript, you've probably seen almost all of this before, but just under a different name. So I'm hopeful that a lot of what we're doing with graphs actually appeals to a broader software engineering audience eventually, once we can kind of make those associations. There's some pretty good primary sources. One of the best out recently is a friend of mine, Juan Sequeira, who went to school at UPM. Juan and Claudio Gutierrez have one of the best surveys of the history of this area for ACM that they did recently. There's also a survey paper from 2 years ago by Ed and Hogan, about 20 authors on that, but it's a really good one. A couple of friends of mine at Google, Natasha Noy and Derwen McGinnis, they wrote the foundational paper in this called Ontology Development 101. They did that when they were grad students back at Stanford about 20 years ago. And really, you can find knowledge graph practices going back in the literature a long ways. One of my favorite scientists ever, Charles Sanders Peirce, he wrote about something called existential graphs in the 1880s. So, there's definitely a lot of research and thinking that's gone into it. The current practices, though, there's a whole body over on the semantic web, W3C kind of standards. And those are very useful, but in contrast, then there's something that's much more popular in industry called label property graphs, coming from Neo4j and others. There have been efforts to try to align these. So there's something called RDF star, and there's a general graph query language, and there's been work on this going on for the past 10 years, and based on the latest PRs, it'll probably be another 10 years or so before it's ready. But there are many other kinds of graphs, as we'll show, and there are other ways that you can actually align some of these parts, which hopefully we can talk about. So this is a great survey out of Google talking about what they do internally. There's usually not a lot of info, but for their graph work internally, they use something called path query. And the path query team did a review. The W3C work generally uses Sparkle as a query language, very popular. The labeled property graph community generally uses Cypher as a query language, again, stemming from Neo4j and all. And then there's also been work on more of a programmatic approach, Apache Gremlin. So Marco Rodriguez and others had done that. Those are the three main things in industry. But Google came up with path query, and it actually has more constraints than the other languages. It's actually less capable, if you will. But what it implies, though, is it's actually much higher performance on distributed systems at scale. And so by doing a few constraints on how they manage these queries, they're able to come up with overwhelmingly better performance. So I do think that going forward, we'll see a lot less things that look like Cypher and a lot of things that look more like path query. I've been working with some other colleagues. We have a curated list of all the available vendors in this space. There are over 50 different graph database vendors currently, and we are very eager to put more onto this shared document. So, we're definitely working with vendors to try to represent them fairly and tracking it. It's interesting because almost all of the vendors are very focused on database. In fact, they're focused on transactional databases. So even though they want to do really large-scale graphs, they want to provide for atomic acid kind of compliance, if you will. There's not a lot of work in terms of providing for scale, horizontal scale-out. And so it's a little bit of a disconnect between what's needed in business, because if you go to a large enterprise firm, they already have SAP and Oracle and IBM, and they have a lot of database management. They don't need other databases. That's one of the first things they'll say. What they do need, though, are practices for horizontal scale-out of the compute. They need to support streaming, because more and more they're seeing streaming data cases. They want to leverage things like event sourcing. So, this would imply something much more like, say, Apache Pulsar. There's a little bit of a disconnect here in this area. And it reminds me of, I did a lot of work with Apache Spark years ago, and from about 2008 to 2015, there were very popular products called MPP. There was a number of different vendors who had scalable SQL databases that ran on top of Hadoop. And they were quite the rage. And there were a lot of them, and they were heavily funded. And then Apache Spark came along, and in about 2014, 2015, they just wiped out that whole area. The top 3 vendors in this space, their publicly traded stock dropped 40% overnight this 1 week. So it's really interesting because you see sometimes where in IT industry the vendors will all go in one direction even though their customers are asking for something different. And that definitely happened in big data back in about 2015. And I think it's also very much poised to happen now in terms of graph. And it'll probably be driven by hardware. Okay, I want to make some progress here. I'm going to skip through. But just roughly speaking, there's still this cognitive bias that also that if you ask people to describe data, they'll come back and they'll talk about rectangles. They'll talk about rows and columns. They'll talk about spreadsheets. They'll talk about a matrix. Realistically, though, if you do look at spreadsheets, they're based on dependency graphs internally. They go to a lot of extent, not to show the dependency graph, but they rely on it. Same thing with SQL. With relational databases, they utterly depend on having a very complex graph for the query plan, the DAG, and also for the schema, the ERDs. But they go to great lengths never to show that. And the thing is that the metadata and the business rules that both spreadsheets and SQL rely on, they tend to get buried. And this has led to a lot of problems, a lot of tech debt. Trying to force data, which is actually a graph, into the shape of rectangles, it leads to IT problems, compliance issues, risks, et cetera. Now, what we find fascinating is that up until about a year and a half ago, Gartner really wasn't very keen on using graph technologies. They were basically saying some pretty bad things about it. In February of 2021, though, they did an abrupt about face, and they came out and they said, look, 50% of the queries coming in about AI that they get are customers asking about graphs. And in their estimate, 80% of data science will be captured by graph data science before 2025. So they're seeing this area really expand rapidly. And the last paragraph is why. Graphs expose the metadata and the business rules, which were otherwise swept under the rug, which are very difficult to get at if you're working with spreadsheets or even with SQL systems. But graphs put this forward, and they put it forward in a way that can really be leveraged along with the domain experts. That's the important part. That's where this is really so different. So as far as use cases, I can show a few. A lot of it has to do with motifs and working with uncertainties and complexity. Frankly, these areas here of cycle detection and disambiguation, these are basically data preparation, but they're the hardest part usually. That's what takes the longest. And it's still difficult in industry because usually IT is pushing back. They don't want to have different systems. They want you to use their data lakehouse instead. And the other thing that we find is that in business, once you start doing a graph practice, you run into trouble with the executives because you might start out with some customer data, and that's one division, and then immediately you need to bring in procurement, and that's a different division. And then you start to bring in some of the R&D and maybe some of the market intelligence people, that's a different division. Suddenly you have 3 SVPs saying, hey, wait, your IT system is cutting across my territory. And so this is the biggest problem we have in industry right now is the executives try to kill these projects because they take away responsibilities that they would like to keep. But it speaks, if you've been following anything about, say, data mesh, it speaks to what a lot of the data community is talking about in terms of data mesh. So as far as examples, I tried to provide videos for most of the, or papers for most of these. I'll just point out 2. If you haven't seen it, I highly recommend Albert Laszlo Barabasi and this new field that they have called network medicine. I don't know, how many people have seen Barabasi's talks? Anybody here? So, okay, just to put this short, this is groundbreaking in terms of AI and medicine now. In the US, we have the Food and Drug Administration that they regulate health and food and that kind of thing. And the FDA came out with a list out of all the molecules that they're interested in that show up in our food supply. There are 150 top molecules that are regulated. So if you provide food, if you sell it and it has one of those molecules, then you have to show how much of those ingredients are there, whether it's sugar or salt or whatever. 150. But realistically, in terms of food supply, there are more like about 3,000 kinds of molecules that show up regularly in the food. As it turns out, if you look at genomic research for cancer, if you look at gene expression, the top 150 molecules that are being regulated by the FDA are not really the most important part. Instead, it's the secondary molecules where they have relations between them, they have interactions. Those are the ones that trigger cancer. So what Barbassi's team has done is to build out large-scale graphs that take into account thousands of molecules and hundreds of thousands of different types of food, and then all the different gene expression, and then looking into cancers, et cetera. So you can drive toward much more personalized medicine. And they've disproven what the regulatory environment was looking at. It's really groundbreaking, and we're already starting to see some medical spin-offs from it. Another one is related. The second one is Stephen Reiling, and I highly recommend the YouTube video from Novartis. What they did was, they make drugs, and they want to retarget some of their existing drugs and find out where they can be applied. What they did was to go back to PubMed and the other places where papers are being published about medicine and pharmacology. And they took the whole stream, hundreds of thousands of research papers coming in, and use NLP to be able to extract entities. And then, given that mentions of different molecules or different genes or different diseases are being made in the same paper, they just take that as a very simple association. That paper has these entities, they're related. And they take all of that and organize it into a graph. And then they apply a simple model that basically has groups of molecules for drugs, basically, and then groups of genes, and then groups of diseases. So they can probabilistically, from all the research coming in, define a graph that shows some of the shapes, some of the patterns emerging between drugs and gene expression and disease. And what they did was then to build out ways, AI applications, to describe, here's how we could prioritize research, steering toward addressing certain types of genomic diseases to affect, or genomic conditions to affect certain diseases. And the funny thing, the hilarious part was they went to their biologists and they said, look what our AI system produced. And the biologists laughed, basically. And they said, look, what you're showing us, 80% of this, we already know this. This is what we do every day. And the computer science people went back and said, well, what about the other 20%? And the biologist was like, nope, never seen it before. So they started using this. Novartis has used this approach then to prioritize their wet lab research. And what they found was that 20% that they hadn't seen before, a lot of new drug discovery is actually happening right there. So this is a really compelling area of being able to leverage graphs and AI techniques. Again, going back to graph neural networks, being able to do this kind of like link prediction and other techniques to suggest where's the 20% that the domain experts really want to see that they've never been able to see before. And we work in manufacturing, BASF, and we have friends at Siemens and Bosch and others, and they have similar kinds of problems when they're talking about global supply networks and material science and the other things that they do. I know I'm running out of time, so I want to move forward. I just want to give a little bit of a flavor here. When you build a graph, you don't go from the top with a large enterprise knowledge graph. You usually start with a middle-out approach, where maybe one business unit gets success. So let's say we start with customer orders, bill of materials, and you have part numbers and things like that. And then you add to it, you expand out with some vendor data. So you have your supply network here. Where do those parts come from? And then you start to look at other factors. Maybe there's regulatory compliance in terms of carbon footprint. That's a big thing in manufacturing, especially in the EU. So, now we bring in, factors in terms of the different carbon footprint for the different vendors and what are their sustainability practices. And then we can add on maybe some market intelligence. So we can take shipping manifests, IP filings, environmental impact reports, where we've lost bids, where there's M&A activity amongst vendors. And we start to get this big picture, sort of a digital twin of how the whole business is working. But again, going back to like what Novartis showed and what we're seeing over on the life sciences side, we're taking and applying those same kind of ideas, but in manufacturing. And just to summarize here, if you've got a simple problem, a spreadsheet's probably good. If you've got a more complicated problem, data lakes and business intelligence, that's the known unknowns. But when you get into these complex problems like global supply chain, you must be able to sense patterns. And this is where graph neural networks excel. You're working with unknown unknowns, and you probably need a graph. I'm out of time. I'm just going to say there's a project we have called KG Lab that is a Python open source abstraction layer for a lot of other open source projects of graph technologies. There's a few similar things like GraphScope out of China and KGTK. Ours is used in industry, so we get sort of trial by fire at scale. We've done a lot of integrations. We have a lot more planned, but it's mostly about making the graph technologies speak PyData and be able to work on distributed systems. And also just leveraging the math and providing those transforms between the numeric and the symbolic. And that's how we're able to do the integrations. And I'm not going to go into detail, but whether you're building a graph or storing it, we've been partnering, like we're partnering with UPM on their Morph project. We've been trying to do a lot of integration work here and make this something that can be more useful in business. We also have about a dozen different notebooks, and also there's a container on Docker Hub. So if you want to try and work through, there's a lot of material here, but we have a tutorial that's based off of food.com showing how to apply like 250,000 recipes and do some graph analytics on it. I will say that one of the findings we've had is just how well Parquet and Arrow and Pulsar fit toward this whole ecosystem and how much they've been overlooked before, but orders of magnitude speed up in terms of serialization. Literally, one of the problems we had, one of our customers with Neo4j, it was taking them 2.5 days to load a graph. And we used Parquet on it instead, and we were able to bring that down to about 38 minutes. And that was even before we started using the GPUs on it. A lot of great work in visualization. Graphistry is a company we've been partnering with. And just trying to make this more Pythonic, I guess you would say. But like, for instance, really close integration with cuGraph for rapids. And we still have some work in progress on the neural network side, but here's an application of using neural networks for doing some link prediction there. The thing that I'm really excited about, though, is what's happening in statistical relational learning. This is where you get into like Bayesian networks and causality. I'm particularly impressed with work by Lise Couture and her team out of Santa Cruz on something called PSL. There's also work out of South Africa from IBM called LNN. But we believe that for representing uncertainty, this is going to be crucial, and we've been working on this integration a lot. Also, there's some great links if you want to look into the slides. We've got a LinkedIn group that's up to 500 people now. There's the KGC conference that has 2,000 people on Slack, and really a lot of activity. In London, there's the CDW conference. We also work with them. They're also really great. And of course, everybody's hiring, but here's our friends hiring. And with that, if you want to get a hold of me, there I am. And I'd love to take some questions if you have anything. Thank you very much. How are we on time? Can we take a few questions, or should we? If you have some questions, we'll take those. We'll go ahead. Yes? No? Okay. Anybody here working with knowledge graphs? I should ask that first. Let me ask some questions. Okay, good. Was that a reasonable representation? Does that fit? Okay.
Hi, Paco. Thank you for your presentation. One question. what is your recommendation with a small company that is having simple queries database to present some dashboards to move to the complex scenario? What is the roadmap that you recommend for this kind of situation?
Interesting. There's a great project out of UPM in Madrid. Oscar Contra is leading. He's a professor leading that. There's a project called Morph, and it's a way of defining rules to import from a relational database to build out a knowledge graph directly from your relational data. That's something we've worked on. Actually, their PhD students are doing the commits on our project. So I look forward to more of that kind of scenario where a business can take and start to model their data in more automated ways to be able to bring it into a graph format. Having said that though, I'm a big fan also just a lot of what we do is in memory. I find that for the graph computation, it really is kind of memory bound when you really look at the hard problems. So if you have a kind of data requirements where you could be running in memory, you can generally get much better performance. And so for things like that, NetworkX and cuGraph and all, they're very good for being able to do more of the algorithmic side of things. But I think really to answer that kind of question, the first step, I would go back to the first part of the talk, thinking about, about graph thinking. It's like conceptually, how do you perceive the problem? And that approaching it more from how the domain expert thinks about the problem, as opposed to how does the IT professional think about it. I think that's the crucial part. Because what we're finding over and over again when we go out and work in industry is, they've got this huge SAP system, and IT says, oh no, you can't do that, you can't do that. But some business leader, she's sitting there saying, no, this is what I must do. And so we work directly with the business people, and we get them set up, and probably work around the data lake. Probably, we do some imports, but we don't use it otherwise. So I think that's really the first step, and probably where the most efficiency is to work with the business, the domain people first. And in our case, we've been working in chemistry a lot. We work with chemists, 10,000 chemists at BASF, and trying to describe what their industrial recipes are, and then what their supply network looks like, and other factors that we build out. And it's been really interesting talking directly with these incredible chemists who know nothing about computer science. And actually, what I would recommend, what we've done is, have you ever seen these products you can get called mind maps? You can do like some type of illustration. If you can get a domain expert to be using a mind map just on their laptop or on a website, that's usually a first good step. And once they can describe that, then you can start to work in the automation, work in the technology. Does that help?
Yes.
Great. Okay, any other questions?
Yeah, here. Yeah. What I always found as a practitioner working with clients with these technologies is that when you see the end result on a specific use case, the result is usually amazing. So you visualize a graph and suddenly, you see everything clear. But when you try to do it on a new use case, there is a lot of hard work to get that wow moment. So you have to have really clear the question you're looking for before you're going to endeavor all that effort to try to get it out of these graph technologies. So it becomes like a chicken and an egg problem, because most of the time you don't have the question ready from the beginning.
Yeah.
So that has been a blocker for me to use this kind of technology, or to build products that people are going to use by themselves with these technologies. So do you have any comment or recommendation in that direction?
Yeah, it's really interesting working in large enterprise where they have a lot of money and they can afford to buy all kinds of systems. And what we've seen is that some of the projects, all they did was just a nice visualization. That's as far as they could get. And the executives look at it and go, wow, this is incredible, we should get these framed. But they can't, they have no takeaway. What we've done instead, more recently, how we've tried to address that, is to actually get the business teams in a room at a blank whiteboard or on a laptop with like mind maps and get them to describe their problem and say, okay, what's the starting point that you have? Draw a circle around it. Okay, and now where are some of your goals? Draw a circle around that. And then how are these connected? And they draw a line between the two circles. And then you're like, okay, what other data do you use to make your decision? And they start drawing other nodes and circles. And soon they have a graph up at the board. And at least they're thinking in that direction. And so once they're thinking in that direction, then they're thinking about what are the patterns they're trying to perceive, what are the outcomes that they need. And then we can use that to take the experts in ontology and distributed systems and all the rest and start to be much more goal-oriented. Because otherwise, these projects can just be horrendous. They can be ontology work for 5 years, and you get nowhere. But again, going directly to the domain experts and saying, look, you're going to teach me about computer science or about chemistry. I'm going to teach you about computer science. Together, we'll do something. It'll be a product. That's really the only way we're making much progress. And the other side of this, of course, is once you load the full data and you've got 5 billion elements and 100 billion edges, and you've got order n cubed algorithms. Literally, we've seen some jobs that run on the order of like 7 weeks to run a job. So there's not a lot of rapid turnaround. So you want to be very careful how you move forward on that, right? Because otherwise, they'll see nothing. But if you can get into a tight loop with some visualization and some algorithmic output, what we find is that typically the domain experts, they'll recognize the outcome right away. So like case in point, if you have a supply network problem, and I can't go into a lot of detail, but there are some where, how should we say, some of the supplies were coming from Russia. If you have that kind of large global scale problem, and you do really naive approaches to a person just throws it into a visualization, they end up with a pretty picture that doesn't mean much. But if you can apply the mathematical transforms so that, okay, we have a way of tracking what goes from a particular class of inventory warehouses to a particular class of subsidiaries that maybe are interchangeable. When you can apply some more of that kind of organization, usually, it's a matter of seconds before the SVP in charge of that area says, oh, yeah, you just showed the problem that we have. Yeah, that warehouse in Brazil has been constantly a problem. They're shipping back and forth to their neighbor. They never ship anything to a customer. They just ship to the other warehouse. Again, it's kind of a difficult path to walk, and there's not a lot of tooling yet, but at least we do have some pretty good practices. And when you can at least work closely enough with the domain expert, they will probably be able to identify the takeaway. I see in this space, I see a lot of low-code and no-code tools coming out in the graph space, and I think it's disastrous because, again, given the complexity, you could be leading a customer to just run something that will not come back with even the first answer for 7 weeks. So you really do need to have people on the team who understand DevOps and understand distributed systems, but you need to have people who understand graph theory as well. And if you can put them in front of a domain expert, it kind of goes back to really old school notions in data science where you had a team of interdisciplinary people. That's the only real way we've been able to solve anything. But, great question. I should give time up to Amparo, so thank you very much.